This video is just extra practice, okay? So we're not going to introduce new concepts necessarily, but get practice with those older concepts for discrete random variables. A new example, okay? So the best way to go through this video is to actually pause it again and just see how much you can get through. The first one might stump you. So maybe you watch the first one if you get stumped and then try to do B, C, D, etc., okay? The next page will be more difficult for sure, so maybe you want to do that one together, but I'd still recommend trying it first, okay? Pause the video and try to see how much of this practice sheet you can get through on your own, and then we'll look through it together. All right, so we have a probability distribution. What did that mean again? A description of the randomness. It lists all the values and their probabilities for the number of repair calls that an appliance repair shop might receive during an hour. It's not certain. In the upcoming hour, maybe they'll get 0, 1, 2, or 3 calls, or maybe more, but we're going to simplify the situation here. Okay, and we're not going to know how many calls they're going to get until it actually happens. It depends on randomness. It's a random variable. So first, letter A tells you to complete the table because there's a piece of information missing. Now, this is not a choose your own adventure math problem. There is one exact right answer. Why? We alluded to it a little bit here. Probabilities should always add up to 100%. They should add up to 1. So what does this need to add up to? It needs to all add up to 1. So the stuff on the left adds up to 0.8, right? That tells us that there must be a 20% chance of getting 3 repair calls. The probabilities should add up to 1. Each probability is some number between 0 and 1. And that's how we can do it this way. So what's the probability that this place gets 2 repair calls? Well, we just did that like the first video. But first we need to say, oh, we don't need to say it. They say it right here. Let X be the number of repair calls they get in an hour. So the probability that they get 2 repair calls is just a probability that X is 2. And again, there is shorthand for here. Just a probability of 2. And we're just going to read the table and say the answer is 40%. That's it. Probability that at least 1 repair call looks like this. And that's going to be 0.9. At least 1 repair call is all of these probabilities. 1 or 2 or 3. We add up the probabilities because it's or, they're mutually exclusive. At most 2 repair calls looks like this. And 2, 1, or 0 repair calls. And again, we added that up earlier. That's an 80% chance. Now, fewer is very similar, but not quite the same. Fewer than 2 is going to be strictly less than 2, not less than or equal to. So 2 is no longer included. Fewer than 2 repair calls now means only 0 or 1 repair call. And the answer will be 0.4. So watch out for that language. How many calls should this shop expect per hour? Now, we could take every value, multiply it by its probability, and then add up all of those products. Or we could use our spreadsheet. It's up to you. So what does that look like? Well, let's get rid of all of our x's and probabilities. We need new x's and we need new probabilities. X could be 0, 1, 2, or 3. Type that in here. We can leave this blank. The probabilities are 0.1, 0.3, 0.4, and 0.2. Now look. See what just happened? All right, we checked that our probabilities added up to 1. That's good. It automatically calculated all of our x times p of x. It already added them up. It automatically calculated all the x minus mu squareds times p of x. Added all of those up, we have the variance, and we took the square root, and we already have the standard deviation. We set up our spreadsheet so that we can put any probability distribution in here, any X values, any probabilities. We could add new rows if we needed to. And it just calculates it for us just like that. Thank you, computers. You could do it by hand too. It's fine. But this should reduce the tedium a little bit. All right, so the expected value is about 1.7. About 1.7 include units. What does that mean? Well, the units of means and standard deviations are always going to be the same units as X. If X is the number of calls, we expect about 1.7 calls in an hour. Closer to 2, but there we go. What's the standard deviation? Well, we just calculated that. This was the variance. This is the standard deviation, sigma, 0.9. 0.9 calls. And again, we could put that all in a sentence. That at this call center, we expect to receive, 1.7 calls, about 2 every hour, and then, plus or minus 0.9, or you could say about 1 call. Okay. I'm not super picky on whether you round to these. Some people might be, but that's exactly what we have going on here. So we expect about 2 calls. Maybe that'll vary by 1 call above, 1 call below. On average, could vary by more, but this is what to expect. And that's how we tie it all together. Now, the next example is a little bit trickier. I still recommend that you try it. And then we can go through it together. So pause the video, give it a shot. See what you got. So you're rolling a die, and if it comes up 6, you win $100. Sounds great. If not, you get to roll again. If you get a 6 the second time, you still win $50, not as much, but you still win. Well, $50 still sounds pretty nice to me. And then if not, you just lose. So what are all the probability possible results, and what's the probability of each? Well, what are the results? You could win $100. You could win $50. Or you could lose. What's the probability of each thing? We have to go back to Unit 3. Ask ourselves stuff about probability. So if we roll a single 6-sided die and it comes up a 6, what's that probability? That's how we win. Rolling 1 die, coming up 6. Well, there's 1 favorable outcome, a 6. There are 6 total outcomes, 1, 2, 3, 4, 5, 6. Probability of winning $100 is just 1 out of 6. Now the next one's a little bit more complicated. To get $50, all right, this is just rolling a 6. To get $50, first we have to not roll a 6. Right? And then roll a 6. This is a probability rule, right? Not roll a 6 and then roll a 6. That's and multiplication. Multiplication. I don't know what I said. They're both really clever. They both roll off your tongue. We need to multiply 2 probabilities. So first we have to not roll a 6. That's a 5 out of 6 chance. And then we have to roll a 6. That's a 1 out of 6 chance. We multiply them together because they are independent. Rolling a die at the start doesn't affect the next dice roll. Okay, so we don't have to worry about conditional probability. If they were independent, we'd have to use conditional probability. And then losing, that's going to be not rolling a 6 twice. Oh. Wrong color. So that'll be 5 out of 6 chance for the first knot of 6, 5 out of 6 chance for the second knot of 6, and there we go. So those are the possible results. Those are the probabilities. We could simplify those, right? 1/6. This is 5 out of 36. This is 25 out of 36. Hopefully those all add up to 1. Let's double check. 1/6 plus 5 out of 36 plus 25 out of 36. Neat, as my grandma likes to say. Oops. All right. So we need to declare our variable. Let x equal, what does x represent here? It's your choice. I think there's a very natural choice here. Be the dollars that we win. Then we can make a table of all of our x values and their probabilities. What are the 3 x values? Well, we could win $100. We could win $50. Or we could win nothing dollars. What's the probability of 100? Well, we found that's a 1/6. We found this was 5 out of 36. Found this was 25 out of 36. All of our probabilities add up to 1. We're good to go. Find the expected amount you'll win. That just means take every value, multiply it by its probability, add up all of those products. 100 times a 6th, 500 times 536, etc. Or we can use our spreadsheet. We have 3 outcomes, so we're not going to need this bottom row. Let's delete all of our x's and p of x's. We could win $100, $50, or $0. The probabilities, let's write an equal sign here. If we write 1/6, it does work, but sometimes you get weird things with conditional formatting. I'm going to write an equal sign just to be safe. 1/6. And then this was 5 out of 36. And then this was 25 out of 36. All right. And then we are getting a little bit of weird stuff with that formatting. I'm going to change all of these from default. Oops. From, where is it? More formats. Put these as numbers. And again, you can choose how many decimal places you want to see. Up to you. Excel still shows and calculates all the decimals. It's just a visual thing. And this says that we expect about $23.61. Does this make sense? Well, we have about a 1/6 chance of this, close to a 1/6 chance of this, and close to a 4/6 chance of this. So most of the probability is down here. So if we think about this as a number line, $23 will be around here. That kind of makes sense. Yeah, most of the probability is below that number. And then this is kind of like an outlier. It's going to skew it a little bit, but it's pretty unlikely, 1/6. Yeah, this seems believable. What's the standard deviation? Well, we just calculated that with the spreadsheet, about $38.20. And again, we can get more decimal places. We want to round to the nearest cent, so let's say $38.16. And we could put that in a sentence, right? Say we expect to win, I'm not going to actually. We expect to win $24. This varies by about $38 on average. Should you play this game if it costs $20 to play? Why or why not? Well, we're winning less than $24 on average. If we play this game a long time, it's random. But if we play it a long time, on average, we'll come out about $24 for a win. So if it costs $25 to play, on average, it's going to cost more than we're going to be winning. In the long run, we're going to be losing money. So probably not. It costs more to play than we expect to win. Just like most gambling. So what costs would we have to charge to make this a fair game? Well, we'd have to charge about $23.61. And then it'd be fair because we'd win on average, and not every time. Sometimes we'd win, sometimes we'd lose. But in the long run, we'd come out about even. That would make it fair. That's how you do it. Let me know if you have any questions on these examples. Hopefully this helps clarify some stuff. In the next video, we go on to special kinds of discrete random variables.